Hey guys, welcome back. So in this video we're going to be going over implicit differentiation. And implicit differentiation is a technique that we use when we're asked to derive a function given to us implicitly. And we're going to talk about exactly what implicit is versus explicitly, which is the other type of function that we can have. Alright, so let's go ahead and get started. So here we have that equations can be written in the form explicitly and implicit, right? So we're used to seeing functions in an explicit way. And what does that mean? We're going to say that explicit is going to be an obvious, it's going to be like obvious, versus implicit, it's like hidden, right? And what exactly is obvious, right? Obvious is going to be what the function is. So here we're going to have an example of an explicit form. It's going to be y is equal to 5 minus x. And why is that obvious? Why are we used to that? Because we're used to having an equation that's just y equals something, and then we have x's on the side, right? We have numbers or x's on the right side. That's what we're used to. That is obvious to us, what the function is, right? But something not so obvious is going to be like if I move this x over, and I'm going to have x plus y equal to 5, we're going to call it an example of an implicit form, right? Because here my function is kind of hidden. I have x and y on the same side. I do not like that, and I'm used to having an obvious function in which I just have y equals to something, right? So the idea here is that if I were to want to derive this function, 5 minus x, it would be very easy because I know just the rules that I need to use, right? But if I were to have to derive this function right here, x plus y equal to 5, I wouldn't really know how to with the techniques that I know up to now. I would need to solve for y, which means going into an explicit form, and then I would derive, right? So that is what we've been used to. We've been used to having y is equal to something, and then we take a y prime, we take an f prime of x, we take a derivative when the whole right side is just equal to the same variable. So the idea here is that if we were wanting to derive the x plus y equal to 5, we would go to explicit form. But what if we can't, right? So here we're going to do a little demonstration of between explicit and implicit, right? So here in this case, I have x, y plus y equal to 5. And here, I'm going to try to go from implicit, which is what I have here. Here I'm in implicit form. And I'm going to try to go to explicit, so I can go ahead and take a derivative. So let's go ahead and try to do that. So what I want to do is I want to solve for y equals, right? So we're going to say that obvious means y equals, right? That's exactly what we want. We want to get this in y equals. And the technique that we're going to use is not even too obvious what we're going to do here. We have a y here, and we have a y here. So I'm going to go ahead and factor out a y from both of these. And it's going to leave me with x plus 1 equal to 5. So I factor out a y from both terms on the left side. So I can leave the y by itself. You see, now I have my y by itself. And then I'm going to go ahead and divide by x plus 1. So it's going to be, so I'm going to divide both sides by x plus 1. So that gives me 5 over x plus 1. So now that I have my y equals, I have my explicit form. You guys see how I have my explicit form. So I'm good to go, right? Because I can just go ahead and derive and apply whatever rule you want to go ahead and do that. Whether your quotient rule or you want to bring it up and do a chain rule, it's up to you. But you have what you're used to, what you've been used to do, which is y equals. And now we're going to go check out this example on the right and see how things go. And we're going to go with the same technique of factoring out a y. So we factor out, see how these two have y's. So we're going to factor out a y from both. And that's going to leave us with an x plus y. With an x plus y. And then we're going to set it equal to 5. And then we want to solve for y again, right? Just like we did over here. And we're going to divide both sides by x plus y. So we're going to have y is equal to 5 over x plus y. You see, the issue here is that I still have a y here on my right side. I don't have y equal to just one variable. I don't have y equal to something in terms of x, right? I don't. And that is a problem because I can't go ahead and derive this because I have x and I have y on the other side. So therefore, I need a technique to be able to solve this type of scenarios to be able to take the derivative. So then is when we bring in implicit differentiation, right? So this function, we're going to say it's written implicitly because, or better say this function is implicitly because I don't have y equals. This right here is explicitly, this right here is implicitly, right? I don't have a simple y equals. And no worries, because we're going to have a little step box here that we have to be able to solve these problems. And they're actually not too difficult. So let's go ahead and try a very basic type of example, and all we got to do is just follow our steps, right? So with our step box, the first step of implicit differentiation is just going to be derive both sides, right? Just go ahead and derive both sides. Before, we usually only would derive the right side because the left side would always be f of x, f prime of x, or y prime of x, right? So in this case, we're going to derive both sides. So let's go ahead and do that. So the first term that we have here is x squared. What is the derivative of x squared? Okay, that's going to be just 2x. Okay, we apply a power rule. Now, what is the derivative of y squared? Well, we're not used to deriving y squared, but if we treat the y squared like we treat the x squared and use a power rule, our derivative would be 2y. We just use the same rules that we use for x, we use them on y. But here's the deal. That's doing step 1. But step 2 tells us to apply a dy dx or a y prime, whatever you like better, dy dx or y prime, to all y's when you derive them, right? So in this case, when I derive an x squared, I just have a 2x. Done. But in this case, when I derive the y squared, whenever I'm deriving a y, I'm going to multiply it by a dy dx or a y prime. I'm going to go ahead with dy dx, because in my example, I told you to find dy dx. Okay? And then I'm going to continue. I'm going to have an equal sign. And I'm going to derive the other side now, which is going to be 9. But the derivative of 9 is just going to be 0, because no matter what we're doing, the derivative of a constant is always 0. So we're good there. So we're done with step 1 and step 2, right? We have derived both sides, and whenever we derived anything that had a y, any term that had a y, we applied a dy dx to it. And then we're going to move terms with dy dx to one side. So it's up to you what side you want to move all the terms that have dy dx, right? It's up to you. I always like to go with the left side, right? Because I just have dy dx equals at the end, and that's just the way I like it. But I will show you guys that you don't always have to move it to the left. It's up to whatever you like, and no matter what, the answer is always going to be right if you follow the correct steps. So we're solving for dy dx, right? So if we want to move the dy dx to one side, that means that this guy right here, this 2x, doesn't have a dy dx, so I should move him. And I'm going to leave the dy dx here on the left, and I'm going to move this term that does not have a dy dx to the right. So I go ahead and do that. I'm going to have just a 2y with a dy dx next to it, right? And it's going to be equal to, when I move over the 2x, it's going to be negative 2x. Okay? And then I'm going to go ahead and solve for the dy dx by, which is my fourth step, right? After I moved over all my terms to all my dy dx terms to one side, which I did, I left the 2y dy dx on its own on the left. I'm going to go ahead and just solve for the red. I'm going to solve for the red, which is my dy dx, which is my step 4. So that means that I need to get rid of this 2y right here that I have in front, and I'm going to divide it by both sides, right? So then I get dy dx is equal to negative 2 divided by 2y. I had the 2y multiplying on the left. I'm going to go ahead and divide it on the right. And then I'm going to go ahead and simplify, right? So now that I already solved for dy dx, now that I already solved for my dy dx, I'm done. But there's always the nice tweaking of the algebra that makes the problem finalized, right? Or we have to just clean it up. We're going to cancel these 2's, and it's going to give us negative y over x. That's going to be our final answer. That's going to be our derivative. So in this case, we no longer have derivatives that are just in terms of x and constants. We now have derivatives that have x and y's put together. So that's the idea. Now let's go ahead and do example B, in which we're also going to take the derivative and we're going to apply implicit differentiation. So let's run into this first term that we have here, right? This first term, we have x times y. So we have two functions multiplying together. We have two variables multiplying together. And what does that require us to do? That's going to require us to do a product rule. You guys see that? So we're going to go ahead and do the product rule. And going to do it in blue. And the product rule starts like this. Derivative of the first. Derivative of the first. What is the derivative of x? It is 1. Times just the second, which is just y. Plus derivative of the second. Now what is the derivative of just y? That is 1, but if you're deriving anything with a y, you multiply dy dx to it. So it's 1 times dy dx. Okay? And then now we just multiply it by the first, which is x. Okay, so now we just finished the product rule. So that what we just did there was my product rule. And I need to go ahead and do my plus, derive my plus y. So I'm going to put a plus. And now what is the derivative of y? The derivative of y, it is just 1 dy dx. Okay? The derivative of y is just 1. And then you derive the y, so you multiply by dy dx. And now we're going to equal it to the derivative of 5 because we're deriving both sides. And what is the derivative of 5? It is 0. Okay? So now we did 1 and 2, which we derived both sides and we applied the dy dx to everything that had a y. So now let's go ahead and do step 3, which means that we're going to move all terms that have a dy dx to one side. So let's just, we have two terms here on the left, right? We have this term and this term here on the left. So let's keep every term with a dy dx on the left. Okay? So this term here, 1 times y just gives you y. This term here, 1 times dy dx times x just gives you x dy dx. And I'm actually going to put the dy dx in red because it just helps us identify that our last step is to solve for dy dx. And then it's going to be just plus 1 times dy dx is just going to be simply dy dx, and it's all going to be equal to 0. Okay? And now we're going to leave those two terms with the dy dx, those two red terms with dy dx on the left, and we're going to move over this non-dy dx term of a y to the right. Right? So we're going to go ahead and move it to the right. And by doing that, we're just going to leave our x dy dx on the left plus our lonely dy dx here on the left, and then we're going to set that all equal to negative y because we just moved over the y to the right. So we need to solve for dy dx, right? So in order to solve for dy dx, what we're going to do is we're going to factor out, we're going to see how these two terms, they both have a dy dx, so we're going to go ahead and factor that out. So if I factor out a dy dx, I'm going to do that over here, a dy dx, I'm going to be left with an x from the first term and just simply a plus 1 from the second term. And that's all going to be equal to negative y. Okay? So I just factor it out because they both had it in common. And now my final step that I'm going to do in order to solve for the dy dx, I'm just going to just divide both sides by this x plus 1 here that's kind of in my way. So I'm going to have dy dx is equal to negative y over x plus 1. And that is my final answer. I just have negative y over x plus 1. So you guys see that here when we do implicit differentiation, a lot of the time the derivative part, which was just over here, it was just step 1, wasn't very difficult because we use the same rules that we already know from before, our power rules, our product rules, our chain rules, our quotient rules, the same type of rules. But what's really tricky at the end is going to be the algebra of solving for the dy dx. And so far we haven't seen anything too annoying, but we're going to be increasing difficulty until we get to D, and you guys will see how the algebra at the end of solving for dy dx just gets a little tougher. Alright, so let's go ahead and try an example C, and let's kill it. So here we're going to have to take the derivative of both sides, right? And remember, if we take a derivative of anything with a y, we're going to go ahead and apply a dy dx to it. So let's go ahead and do that. So here, let's take the derivative of the left, which if we see the left side, what do we need to do? we need to do a chain rule because we have a composite function. We have a 3y plus 7 inside, so that's our inside function squared. So that means that, hey, we have a function raised to a power, boom, we got to do chain rule. So let's go ahead and do that. And we do that by first putting our finger over the parentheses and just having a parentheses squared. So we're like, okay, parentheses squared, let's just do a power rule, which means we bring down this power. So it's going to be 2 parentheses to the first power. Okay, now let's put whatever we have in there in the parentheses, which is 3y plus 7. Now let's take our finger out. Okay, we have a 3y plus 7 there. Now let's go ahead and derive this 3y plus 7. So a derivative of 3y plus 7 is going to be, hold on, we're going to multiply by the derivative of 3y plus 7, which is going to be, the derivative of 3y is going to be the constant, right? So it's 3 times dy dx, okay, plus 0 because that's the derivative of 7. So let's just kind of close this parenthesis here and save some space because the derivative of the inside was just 3 dy dx. And now we're going to go ahead and take the derivative of the right side, which we have 6y squared plus 2x. The derivative of 6y squared, we're just going to do another power rule. Let's bring that forward, which is going to give us 12y to the first power times dy dx. And now the derivative of 2x, it's an x, so it's more simple than when we derive y's. It's just going to be 2. So now you see that we have dy dx's on both the left side and the right side. So now it's a little more tricky and more annoying to to solve for the dy dx, which is our last step. But let's go slow and let's just clean up the equation. And by clean up, I mean I'm going to distribute this 2 into both sides. So I'm going to have 6y, and I'm going to have plus 14. And then that's going to be multiplied here by my 3 dy dx. So now I'm going to multiply this 6y plus 14 times my 3 dy dx. So I'm going to go ahead and get, so let's remember that I'm doing this right now, and then this right after. The first term is going to be 6y times 3 dy dx. 6 times 3 is 18. Then it'll be 18y. And then we still have a dy dx. Okay. And then we're going to have plus 14 times 3. 14 times 3, that's 30, and 12, 52. Did a little bit of math out loud there. 52. I lied. 42. And then that would be 42 dy dx, right? And then we have completely cleaned up the left side, right? And we're going to go ahead and just do 2 steps in one here to save some space, because really we have equal to 12y to the first plus 2 with our dy dx, right? And since we got to make all the dy dx's be on the same side, we're going to go ahead and move this 12y dy dx already to the left, because we know we have to put all the dy dx's on the same side. And if we have 2 dy dx's on the left and I have 1 on the right, let me just move that 1 to the left side and have them all together there. So I'm going to have minus, because it was positive on the right, it's going to be negative on the left, minus 12y dy dx, and that's going to be equal to 2. Okay, so now that I have all my dy dx's on the same side, and I have everything on the right side just with not a dy dx, I'm going to go ahead and factor out a dy dx from all of these. So you guys see how factoring out a dy dx is a very common term whenever we have to solve for dy dx. And let's put that up here real quick, right? So when we say that we have to solve for dy dx, a very common technique is going to be to factor. So make sure to write that down so you guys know that whenever I say solve for dy dx, you're going to be factoring a lot of times. So then I'm going to have a dy dx here on the outside, giant parentheses to put everything that's inside. So it's going to be an 18y plus a 42 minus a 12y, maybe not such a big parentheses, it's going to be equal to 2. Alright? And then I'm going to go ahead and finish solving for dy dx by just dividing both sides by my parentheses. That's going to be another common step that we usually do. It's like a little recipe. We just kind of like derive, and then we just follow the recipe of factoring, then dividing by that parentheses. Doesn't really change much, right? So we're going to have 18y plus 42 minus 12y. But now it's where it can get a little different, because this is a correct answer, but it's not fully simplified. So let's go ahead and do that. Let's go ahead and fully simplify this answer by first combining the 18x and the minus 12x. I mean 18y minus 12y. You're used to thinking about x's. So 2 over 6y plus 42, right? And you would think that we're done because we already combined the y's, but guess what? We're not. Because we can go ahead and factor out a 6 from the bottom. So I'm going to go ahead and do that. I'm going to factor out a 6 from the bottom, and then I get a y plus 7. And then we're still not done, because this 2 and this 6 can reduce, and my final answer is going to be 1 over 3 y plus 7. So that is my final answer right there. That is my dy dx. Alright? So it'll be very important at the end to make sure that you're fully simplified. Because even if you don't simplify in the middle, which I don't really like to simplify in the middle, I just wait till the end, I just fully simplify at the end, your answer will be correct. And not just correct, but fully simplified. Because I'm not saying that the first dy dx we gave was wrong, I'm just saying that it wasn't fully simplified. So let's go ahead and do example D, which it may be a little bit annoying, but just kind of prepares us for the practice problems that are going to come shortly after. So then we look over here at our x cosine of 2y, and that is going to be a product rule. So let's go ahead and jump straight into that product rule, in which we start off by deriving the first. Derivative of x is just 1. I'm not deriving any y, so I don't need a dy dx. I'm good. And then I'm going to have to just multiply the second, which is cosine of 2y. Just keep it there, chilling, relaxing. And then I'm going to add the derivative of the second. But what is the derivative of the second? See, the derivative of cosine of 2y, cosine of 2y itself is it's a chain rule, because we have that 2y inside. Don't forget that. Remember, now we're just always having chain rules just hidden everywhere. So the derivative of cosine by itself, the outside function, the outside layer of this onion, it's going to be simply just negative sine of 2y. And we haven't derived the y yet, we just derived the sine function, right? So we don't need to do y dx, we just derived a sine function. I mean a cosine function that gives us a sine function. And it was a negative sign because it's part of the 3c's rule, which means that a 3c's rule derivative is always negative. So now we multiply by the derivative of the inside, and that is going to be the derivative of 2y is just 2, but you're deriving a 2y which has a y in it, so you get 2 dy dx. Alright? And now we finish by multiplying it by the first, which you multiply by x. And now we're going to equal this to the derivative of the right side, and the derivative of the right side actually comes out quite simple, because the derivative of y is just 1 times dy dx, and we don't even worry about this plus 1, because the plus 1 derivative of that is just going to be 0. So now let's go ahead and kind of clean this up a little bit before we go ahead and do anything. And the first thing I want to clean up was going to be this plus and this negative here, and possibly bring this constant and this x to the front. So we're going to have cosine of 2y minus 2x sine of 2y attached to a dy dx, and that's going to be equal to a dy dx, right? So in this case, we see that we have just brought the 2x to the front, and we have kind of just simplified our dy dx's, right? So now we have to solve for dy dx, or move dy dx to one side first. So here we have 1 dy dx on the left and 1 dy dx on the right. So just to prove to you guys that you don't need to actually have dy dx's all the time on the left, you can actually have them on the right and still get the right answer. Let's go ahead and move this dy dx, this one with the 2x sine of 2y, to the right side. And why do I want to do that? You see, because I have a negative here, so when I move it over to the right, it's going to be positive. So I like positive things. And also, I'm only moving over one term, because if I move this guy to the left, then I need to move this guy to the right. You know? So let's just move one term. And then that means, to be lazy, we're just going to move this one term, this whole term here, to the right. So this is not something different. We're just solving for it with dy dx a little different. Just to tell you guys and give you guys enough comfortable skills to be able to solve for dy dx on the left or on the right side, depending on what's easier to you in the problem. So here we're going to have just dy dx. And then we're going to have plus 2x sine of 2y times dy dx. Alright? And now we're going to go ahead and solve for dy dx by factoring out dy dx. So that means that we're going to factor out dy dx by having dy dx factored out. And then the first term is going to leave us with a 1. The second term is going to leave us with a 2x sine of 2y, right? And then our last step to solve for dy dx is just going to be divide both sides by dy dx. So we still have our dy dx here. And we're just going to make some space to divide everything here on the left side, which is different from what we've been doing because we've been doing everything on the right side. So let's go ahead and do cosine of 2y over 1 plus 2x sine of 2y. So there isn't anything crazy that we could do here to simplify, so we're actually done. So if you really are like really annoyed by this dy dx being on the right, it's alright, you have the right to be annoyed. So let's go ahead and just move it. We're just going to go ahead and switch it, in which we have our dy dx here on the left, and then we're just going to have our answer on the right. Alright, so there we go. So now we have finished solving some implicit differentiation problems. So remember, the idea here is that we're just going to follow our step box, which starts off with deriving both sides of the equation, and then if you're deriving any y's, you make sure to multiply by dy dx. And then we move over dy dx's, all terms that have a dy dx to one side, and then after we solve for dy dx, usually by factoring out a dy dx from all the terms, and then we're going to divide whatever's left to the other side. And now we're going to do some practice problems to see if how you guys understood this skill. So, see you guys next time.